What if a hidden side of Pluto held astonishing secrets? A world cloaked in perpetual twilight, where the landscape is dotted with icy mountains and vast plains, and mysterious geological activity is afoot. What incredible discoveries await in this shadowy, unexplored region? Prepare to be amazed by the breathtaking revelations from Pluto's far side, an extraordinary place unlike any other in our solar system. In 2006, NASA launched the New Horizons spacecraft, embarking on a historic journey to unlock the mysteries of Pluto and its moons. This ambitious mission aimed to provide humanity with its first close-up look at this distant dwarf planet, located over 3 billion miles from Earth in the Kuiper belt, a vast region of our solar system filled with icy bodies and remnants from its formation. New Horizons, traveling at a staggering speed of over 36,000 miles per hour, took nearly a decade to reach its destination. As it hurtled through the void, it gathered crucial data, not only about Pluto, but also about other objects in the Kuiper belt, offering unprecedented insights into the outer reaches of our solar system. The spacecraft's arrival at Pluto in July 2015 marked a monumental achievement in space exploration. For the first time, scientists were able to glimpse detailed images and data of Pluto's surface, revealing a complex world with mountains of water ice, vast plains of nitrogen ice, and a hazy, layered atmosphere. However, the journey did not end there. The most tantalizing aspect of this mission was yet to come: the exploration of Pluto's far side, a region perpetually hidden from direct view from Earth, shrouded in mystery and scientific intrigue. The exploration of Pluto's far side is not just a pursuit of curiosity, it holds profound scientific significance. This remote and enigmatic region offers a unique laboratory for understanding the processes that have shaped not only Pluto, but also other similar bodies in the Kuiper belt and beyond. By studying the far side of Pluto, scientists hope to uncover clues about the planet's geological history, its atmospheric composition, and the broader dynamics of our solar system's outer frontier. One of the most compelling reasons for exploring Pluto's far side is to gain a deeper understanding of its geological diversity. Unlike the near side, which has been relatively well mapped by New Horizons, the far side remains largely unexplored. This area is expected to harbor features and phenomena that are starkly different from those observed on the near side, potentially revealing new insights into the planet's geological processes and history. For instance, scientists are particularly interested in studying the distribution and composition of the ice on Pluto's far side, as it could provide critical information about the planet's climatic and geological evolution. Moreover, exploring Pluto's far side can shed light on the broader context of planetary formation and evolution in the outer solar system. The data gathered from this region can help scientists refine their models of how dwarf planets and other Kuiper belt objects have formed and evolved over billions of years. This, in turn, can enhance our understanding of the early solar system and the processes that led to the formation of the planets, moons, and other celestial bodies that we observe today. Another important aspect of studying Pluto's far side is its potential to reveal new information about the planet's atmosphere. The far side, with its prolonged periods of darkness, experiences different thermal conditions compared to the near side, which could influence atmospheric dynamics and composition. By analyzing the data from this region, scientists can better understand the behavior of Pluto's thin atmosphere, including its interactions with the surface and its response to the planet's extreme temperature variations. In addition to its scientific value, the exploration of Pluto's far side also has a profound impact on our broader quest for knowledge and discovery. It symbolizes humanity's relentless pursuit of understanding the unknown and pushing the boundaries of what we know about our universe. Every new discovery on Pluto's far side adds a piece to the puzzle of our solar system's history, enriching our collective knowledge and inspiring future generations of scientists and explorers. The history of the New Horizons mission is a testament to human ingenuity and determination to explore the farthest reaches of our solar system. The idea of a mission to Pluto began to take shape in the late 1980s and early 1990s as scientists and engineers recognized the unique scientific opportunities offered by this distant, icy world. Pluto, discovered by Clyde Tombaugh in 1930, remained largely a mystery for decades, with only the most basic details known about its size, orbit, and surface composition. In the early 2000s, NASA's Pluto-Kuiper Belt mission received a significant boost when it was selected as the agency's first New Frontiers mission, a program designed to explore the solar system with medium-class spacecraft missions. The mission, later named New Horizons, was formally approved in 2001, with the Southwest Research Institute (SWRI) and Johns Hopkins University Applied Physics Laboratory (APL) leading the charge. Dr. Alan Stern, a prominent planetary scientist, was appointed as the mission's principal investigator, and he, along with his team, began the monumental task of designing and constructing a spacecraft capable of making the epic journey to Pluto. The New Horizons spacecraft was an engineering marvel designed to operate in the harsh and remote environment of the outer solar system. It was equipped with a suite of sophisticated scientific instruments that would allow it to conduct a comprehensive study of Pluto and its moons. A combination of a visible and infrared imager spectrometer, RALPH was designed to capture high-resolution images and color maps of Pluto's surface. It played a crucial role in identifying the various geological features and compositions on the dwarf planet. An ultraviolet imaging spectrometer, ALICE, was used to analyze the composition and structure of Pluto's atmosphere. It helped scientists understand the escape of atmospheric gases and the interaction between the atmosphere and the surface. REX was designed to measure atmospheric composition, temperature, and pressure using radio waves. It provided valuable data on the thermal properties of Pluto's atmosphere. LORRI was a high-resolution telescopic camera that captured detailed images of Pluto's surface. It was particularly effective in mapping the planet's terrain and identifying geological features. SWAP measured the interaction of Pluto's atmosphere with the solar wind, helping scientists understand how the solar wind affects the planet's atmosphere and surface. PEPSI analyzed the energetic particles escaping from Pluto's atmosphere, providing insights into the planet's atmospheric composition and dynamics. 1. SDC, designed and built by students at the University of Colorado, measured the density of dust particles in the outer solar system. This data helped scientists understand the environment through which New Horizons traveled. New Horizons was launched aboard an Atlas V rocket from Cape Canaveral Air Force Station in Florida. The spacecraft set a record for the fastest launch speed of any spacecraft, leaving Earth at a velocity of about 36,000 miles per hour. One of the critical milestones of the mission was the gravity assist flyby of Jupiter. This maneuver provided New Horizons with the necessary boost to reach Pluto more quickly, reducing the travel time by several years. During this encounter, the spacecraft conducted a detailed study of Jupiter's atmosphere, magnetosphere, and its moons, capturing stunning images and valuable scientific data. To conserve energy and ensure the spacecraft systems remained in optimal condition, New Horizons entered a series of hibernation periods during its long journey to Pluto. During these times, most of the spacecraft's systems were powered down, with periodic wake-ups for system checks and course corrections. As New Horizons neared Pluto, it began its approach phase, gradually increasing the frequency of observations and data collection. This phase marked the beginning of intensive scientific operations, as the spacecraft started capturing detailed images and measurements of Pluto and its moons. The culmination of the New Horizons mission came on July 14, 2015, when the spacecraft made its closest approach to Pluto, passing within 7,800 miles of its surface. This historic flyby provided humanity with the first detailed images and data of Pluto, revealing a complex and diverse world that exceeded all expectations. The flyby also allowed New Horizons to study Pluto's largest moon, Charon, in unprecedented detail. After the flyby, New Horizons continued to transmit data back to Earth, a process that took over a year due to the vast distance. The spacecraft also continued its journey into the Kuiper Belt, where it conducted additional studies of other Kuiper Belt objects, further expanding our understanding of this distant region of the solar system. The New Horizons mission represents a monumental achievement in space exploration, demonstrating the incredible capabilities of human ingenuity and the unyielding desire to explore the unknown. The data and images returned by the spacecraft have transformed our understanding of Pluto and the outer solar system, providing a wealth of scientific insights and inspiring future missions to the farthest reaches of our celestial neighborhood. The moment the first images and data from New Horizons reached Earth, the scientific community and the public were enthralled by the revelations. These initial transmissions marked the beginning of an era of discovery, showcasing Pluto in unprecedented detail. Prior to the New Horizons mission, our knowledge of Pluto was limited to fuzzy images from ground-based telescopes and the Hubble Space Telescope. The spacecraft's approach to Pluto brought the first high-resolution images that transformed our understanding of this distant world. As New Horizons approached Pluto, it began sending back images that displayed a surface far more complex and varied than anticipated. The images revealed a world with stark contrasts, bright, icy regions juxtaposed against darker, more rugged terrain. This was a dramatic shift from the relatively featureless sphere that many had expected. The early images captured the imagination of millions, showcasing intricate patterns on Pluto's surface, hinting at a rich geological history. One of the most striking features observed by New Horizons was the presence of mountains on Pluto's surface. These mountains, some rising as high as 11,000 feet, were primarily composed of water ice. Given Pluto's extremely cold temperatures, where nitrogen and methane are solid, water ice functions similarly to rock on Earth. The discovery of these icy mountains indicated that Pluto's surface is geologically active, with processes reshaping the landscape over time. Another remarkable feature was the vast plains, particularly the region known as Sputnik planitia. This heart-shaped plain, composed of nitrogen ice, stretches over hundreds of miles and is relatively smooth, indicating a young surface. The lack of craters in Sputnik planitia suggested that it is geologically young, possibly formed by recent or ongoing resurfacing processes. The presence of convection cells within the plain, where nitrogen ice circulates and reforms, pointed to a dynamic and evolving surface. Valleys and canyons also crisscross Pluto's surface, adding to the planet's diverse topography. These valleys, likely formed by tectonic activity or the sublimation of surface ice, provide further evidence of Pluto's active geological processes. One of the most notable valleys is Virgil Fossa, a deep trench that cuts across the landscape, hinting at the internal forces shaping Pluto. The discoveries made on the near side of Pluto were filled with unexpected surprises that challenged pre-existing theories about the dwarf planet. One of the most significant surprises was the detection of a thin atmosphere, composed primarily of nitrogen, with traces of methane and carbon monoxide. This atmosphere, although tenuous compared to Earth's, is capable of supporting weather patterns and even hazes that obscure the surface. Another surprising discovery was the presence of a layered atmosphere. Images taken during the spacecraft's departure from Pluto showed sunlight streaming through its atmosphere, revealing multiple layers of haze extending up to 200 kilometers above the surface. This haze, likely caused by the interaction of sunlight with methane, creates complex atmospheric phenomena that were previously unimagined. Additionally, the New Horizons team found evidence of potential cryovolcanism on Pluto. Cryovolcanoes, or ice volcanoes, erupt with a slurry of water, ammonia, or methane instead of molten rock. The discovery of features that resemble cryovolcanic domes suggested that Pluto might have internal heat sources, possibly from radioactive decay or other processes driving geological activity. Wright Mons and Picard Mons, towering ice volcanoes, provided some of the clearest evidence of this phenomenon. The near side of Pluto also revealed surprising color variations. The images captured by New Horizons showed regions with a reddish hue, particularly around the equator. This coloration is believed to be caused by tholins, complex organic molecules formed by the interaction of sunlight with methane in the atmosphere. These tholins settle on the surface, giving it a distinctive reddish tint, and are indicative of complex chemical processes occurring on Pluto. Furthermore, New Horizons discovered an intriguing feature in the form of polygonal patterns on the surface of Sputnik planitia. These polygons, each several tens of kilometers across, are believed to be the result of convection within the nitrogen ice. As the ice warms slightly, it rises and then cools and sinks, creating a pattern similar to that seen in boiling water. This discovery pointed to active geological processes that are reshaping Pluto's surface even today. As the New Horizons spacecraft ventured closer to Pluto, it also captured stunning images of Pluto's largest moon, Charon. The close-up views of Charon revealed a surprisingly diverse and complex world with its own mountains, canyons, and plains. One of the most striking features on Charon was the massive chasm known as Serenity Chasma, which stretches over 1,000 kilometers long and up to 9 kilometers deep. This chasm, far deeper than the Grand Canyon on Earth, suggested significant tectonic activity in Charon's past. The New Horizons mission's initial discoveries provided a wealth of information that fundamentally changed our understanding of Pluto. The presence of mountains, plains, valleys, and an atmosphere indicated that Pluto is far from the inert, frozen world it was once thought to be. Instead, it is a dynamic and complex planet with ongoing geological and atmospheric processes. These findings set the stage for further exploration of Pluto's far side, promising even more astonishing revelations about this distant member of our solar system. The far side of Pluto, often referred to as the dark side due to its remoteness from direct sunlight and Earth-based observation, remained a profound mystery for decades. Before the New Horizons mission, our knowledge of Pluto was largely based on distant telescope observations that provided limited and often blurry images. These observations primarily focused on Pluto's near side, the hemisphere that faces Charon, its largest moon, and is occasionally illuminated by the distant sun. The far side, perpetually hidden from Earth due to Pluto's synchronous rotation with Charon, presented a blank slate to scientists and space enthusiasts alike. This mystery was compounded by Pluto's distance from the Sun and Earth. Located in the Kuiper belt, over 3 billion miles from the Sun, Pluto receives only a fraction of the sunlight that Earth does. This results in long periods of twilight and darkness, particularly on the far side. The extreme cold and the faint light make it a challenging target for telescopic imaging, which was further limited by the dwarf planet's small size and slow rotation. Consequently, the far side's surface features, composition, and geological activity remained largely speculative, awaiting the arrival of a spacecraft capable of providing direct observations. Imaging and studying Pluto's far side posed significant technical and logistical challenges for the New Horizons mission. One of the primary hurdles was the need for precise navigation and timing to capture high-resolution images during the brief window of the spacecraft's closest approach. Given Pluto's immense distance from Earth, the communication delay meant that real-time adjustments were impossible. The mission team had to rely on pre-programmed instructions and autonomous systems to ensure that New Horizons was correctly oriented and operational at the critical moments. Another major challenge was the limited power and data transmission capabilities of the spacecraft. New Horizons, powered by a radioisotope thermoelectric generator, RTG, had to carefully manage its energy consumption to ensure that all instruments functioned optimally during the flyby. The vast distance also meant that data transmission rates were extremely low, necessitating the storage of vast amounts of data on board for later transmission back to Earth. This process required meticulous planning and prioritization of which images and data to capture, ensuring that the most scientifically valuable information was obtained. The harsh environmental conditions on the far side of Pluto added another layer of complexity. The region's extreme cold, with temperatures plunging to around 375 degrees Fahrenheit, posed risks to the spacecraft's instruments and systems. Additionally, the low levels of sunlight required the use of long-exposure imaging techniques to capture detailed photographs, increasing the risk of blurring due to the spacecraft's motion. When the first data and images of Pluto's far side began to trickle in from New Horizons, the scientific community was astonished by the unexpected diversity and complexity of this remote region. The initial impressions revealed a landscape that was both familiar and alien, echoing some features seen on the near side while introducing entirely new and enigmatic formations. One of the most striking discoveries was the presence of a vast, dark region dubbed Cthulhu Macula, stretching almost halfway around Pluto's equator. This area, characterized by its dark reddish-brown hue, contrasted sharply with the brighter, icy plains seen on the near side. The coloration is believed to be due to tholins, complex organic molecules formed by the interaction of sunlight with methane in Pluto's atmosphere. The sheer size and darkness of Cthulhu Macula hinted at a long and complex geological history, with potential implications for understanding the distribution of surface materials across Pluto. Another surprising feature was the discovery of what appeared to be ancient, heavily cratered terrains. These areas suggested that parts of the far side surface have remained relatively unchanged for billions of years, preserving a record of impacts and geological activity from the early solar system. The craters varied in size and preservation, providing insights into the impact history and the surface processes that have shaped Pluto over time. In addition to the ancient craters, the far side also revealed signs of more recent geological activity. New Horizons captured images of ridges, troughs, and valleys that indicated tectonic forces at work. These features suggested that Pluto's interior might still be geologically active, with internal processes driving the formation and modification of surface structures. The presence of such diverse geological formations on both sides of Pluto underscored the complexity of this distant world. The far side data also offered new clues about Pluto's atmospheric dynamics. The thin haze observed on the near side extended into the far side, creating a tenuous but persistent atmospheric presence. This haze, likely composed of nitrogen, methane, and other gases, interacts with the surface, influencing both its appearance and its chemical composition. The observation of haze layers on the far side provided a more comprehensive understanding of Pluto's atmosphere and its seasonal changes. One of the most unexpected findings was the detection of potential cryovolcanic features. These formations, resembling domes and flows, hinted at the possibility of icy volcanic activity on Pluto. Cryovolcanoes, if confirmed, would suggest that Pluto's interior contains enough residual heat to support such processes, challenging previous assumptions about the thermal evolution of small, distant bodies in the solar system. Overall, the initial impressions and surprises from the far side data painted a picture of Pluto as a dynamic and diverse world, with a geological and atmospheric complexity that rivals planets much closer to the Sun. These findings have spurred ongoing analysis and sparked new questions about the processes shaping Pluto and other similar bodies in the Kuiper belt. As the New Horizons mission continues to transmit data and scientists delve deeper into the information gathered, the far side of Pluto promises to reveal even more stunning secrets about our solar system's outer frontier. The far side of Pluto, revealed through the high-resolution images and data sent back by New Horizons, showcases a stunning array of geological formations that highlight the complexity and dynamism of this distant world. Among these features, some stand out due to their uniqueness and the clues they offer about Pluto's geological history. One of the most remarkable formations is Cthulhu Macula, a vast dark region extending almost halfway around Pluto's equator. This area is characterized by its dark reddish-brown hue, which is believed to be the result of tholins, complex organic molecules formed by the interaction of sunlight with methane. Cthulhu Macula's surface is heavily cratered, indicating its ancient origins. The craters vary in size and preservation, suggesting a long and turbulent history of impacts. The region's dark coloration and complex surface texture make it a fascinating subject for studying the chemical processes at work on Pluto. Another notable feature is the series of ridges and valleys that crisscross the far side. These formations suggest tectonic activity, where the surface has been pushed and pulled, creating fractures and fault lines. One such area, known as Tartarus dorsa, consists of parallel ridges stretching for hundreds of miles. These ridges are thought to be caused by the contraction and expansion of Pluto's icy crust, possibly driven by internal geological processes or the sublimation and deposition of surface ice. The far side also contains vast plains, similar to the near side's Sputnik planitia, but with distinct differences in composition and appearance. These plains are believed to be composed of a mixture of nitrogen, methane, and carbon monoxide ices. The surface of these plains is relatively smooth, suggesting they have been resurfaced by glacial or cryovolcanic activity. The smoothness of these plains contrasts sharply with the rugged terrain surrounding them, highlighting the diverse geological processes at play. When comparing the unique geological features of Pluto's far side with those of other celestial bodies in our solar system, several intriguing parallels and contrasts emerge. For example, the dark, tholin-rich regions of Cthulhu Macula bear a resemblance to similar organic-rich areas on Saturn's moon Titan. Titan's surface is also covered in tholins, giving it a reddish hue, and its complex organic chemistry is thought to be driven by interactions between sunlight and atmospheric methane. This similarity suggests that similar chemical processes may be occurring on both Pluto and Titan, despite their vastly different environments. The tectonic ridges and valleys of Tartarus dorsa can be compared to features found on other icy moons, such as Europa and Ganymede. Europa, one of Jupiter's moons, exhibits extensive ridges and fractures across its icy surface, believed to be caused by tidal flexing from Jupiter's gravitational pull. Ganymede, another of Jupiter's moons, also shows evidence of tectonic activity, with ridges and grooves resulting from internal geological processes. The presence of such tectonic features on Pluto indicates that, like these moons, Pluto's icy crust is dynamic and subject to internal forces. The smooth plains of the far side can be likened to the volcanic plains found on Mars, particularly those in regions like the Tharsis Plateau. While Mars' plains are formed by basaltic lava flows, Pluto's plains are composed of nitrogen, methane, and carbon monoxide ices, resurfaced by cryovolcanic or glacial processes. Despite the different materials and formation mechanisms, both types of plains highlight the role of surface renewal in shaping planetary landscapes. The formation of the unique geological features on Pluto's far side has intrigued scientists, leading to several speculations and theories. The dark regions of Cthulhu Macula, with their complex organic chemistry, suggest a long history of atmospheric and surface interactions. One theory posits that these tholins are formed in Pluto's thin atmosphere and gradually settle onto the surface, accumulating over millennia. The presence of craters within this region indicates that it has been relatively undisturbed by geological processes, allowing these organics to accumulate and darken the surface over time. The tectonic features of Tartarus dorsa suggest that Pluto's icy crust is subject to internal forces, possibly driven by a subsurface ocean or cryovolcanic activity. One theory is that as Pluto's internal heat causes the ice to expand and contract, it creates stress on the surface, leading to the formation of ridges and valleys. This process is analogous to tectonic activity observed on icy moons like Europa and Ganymede. The possibility of a subsurface ocean raises intriguing questions about the potential for liquid water, and perhaps even life, beneath Pluto's icy exterior. The smooth plains on the far side are believed to be the result of cryovolcanism, where instead of molten rock, volatile ices such as nitrogen, methane, and carbon monoxide are erupted onto the surface. This process could create smooth, relatively young plains, much like the volcanic plains found on other planets. The smoothness and lack of craters suggest that these plains have been resurfaced relatively recently in geological terms, indicating ongoing cryovolcanic activity. Another theory involves glacial processes, where nitrogen and methane ices flow across the surface, smoothing out the terrain. This glacial activity could be driven by seasonal changes in temperature, causing the ices to sublimate and redeposit in different areas. This theory is supported by the observation of flow patterns and other features indicative of glacial movement. The discovery of cryovolcanism on Pluto was one of the most surprising and significant findings of the New Horizons mission. Unlike typical volcanic activity, which involves the eruption of molten rock, cryovolcanism involves the eruption of volatile substances such as water, ammonia, or methane, often mixed with rocky material from beneath a planet's surface. On Pluto, the evidence of cryovolcanism comes from several distinct geological features identified in the high-resolution images and data sent back by New Horizons. One of the most compelling pieces of evidence for cryovolcanism on Pluto is the presence of large, dome-like structures with central depressions, which are reminiscent of cryovolcanic domes seen on other icy bodies. Wright Mons and Picard Mons are two such features, standing several kilometers high with broad, flat summits and central pits. These formations are strikingly similar to cryovolcanic domes on other icy moons, such as Titan and Europa, suggesting that similar processes are at work. The composition of the material around these domes also points to cryovolcanic activity. Spectral analysis has revealed the presence of ammonia hydrates and water ice, substances that are expected to be part of the cryomagma erupted from below Pluto's surface. The detection of these materials supports the hypothesis that cryovolcanism is an active process on Pluto, contributing to the continuous resurfacing and geological evolution of the planet. The relatively young age of the surface around these cryovolcanic features, indicated by the low density of impact craters, suggests that cryovolcanism has been a recent and possibly ongoing activity. This recent activity implies that Pluto still retains some internal heat, possibly from radioactive decay or the residual heat from its formation, sufficient to drive cryovolcanic eruptions. Cryovolcanism has played a significant role in shaping Pluto's landscape, contributing to its dynamic and diverse surface features. The eruptions of cryomagma, which likely consist of a mixture of water, ammonia, and other volatiles, reshape the surface by depositing fresh material and forming new landforms. One of the key impacts of cryovolcanism is the creation of large cryovolcanic domes like Wright Mons and Picard Mons. These structures dominate the landscape with their broad bases and central pits, altering the topography significantly. As cryomagma erupts and flows across the surface, it creates smooth plains and fills in depressions, similar to the way lava flows create volcanic plains on Earth. These cryovolcanic flows can cover older surfaces, erasing impact craters and other geological features, thus contributing to the ongoing resurfacing of Pluto. Cryovolcanic activity also leads to the formation of pits and depressions, as observed on the summits of Wright Mons and Picard Mons. These pits are believed to form when the cryomagma chamber beneath the surface empties during an eruption, causing the overlying material to collapse. This process is similar to the formation of calderas on Earth, where the surface collapses after the eruption of large volumes of magma. The deposition of volatiles from cryovolcanic eruptions can also contribute to the formation of ice-rich regions and the layering of surface materials. As cryomagma reaches the surface and cools, it can create stratified deposits that reveal the history of cryovolcanic activity over time. These layers can provide valuable clues about the composition of Pluto's interior and the processes driving its geological evolution. Cryovolcanism may also influence the atmosphere of Pluto. The release of volatile compounds such as ammonia and methane during eruptions can contribute to the planet's thin atmosphere, replenishing it and potentially driving seasonal changes. These volatiles can interact with sunlight and other atmospheric components to form complex organic molecules, which can then settle on the surface, contributing to the coloration and chemical diversity observed on Pluto. While cryovolcanism on Pluto shares some similarities with volcanic activity on Earth, there are also significant differences due to the vastly different environmental conditions and materials involved. On Earth, volcanic activity is driven by the heat from the planet's interior, which melts rock into magma. This magma then rises through the crust and erupts at the surface, forming lava flows, volcanic domes, and other features. The heat required for terrestrial volcanism is primarily generated by radioactive decay, residual heat from Earth's formation, and, in some cases, the frictional heating from tectonic processes. In contrast, Cryovolcanism on Pluto involves the eruption of volatile ices rather than molten rock. The internal heat driving cryovolcanism is likely much lower than that on Earth, requiring less energy to melt the ices. This heat could come from radioactive decay within Pluto's rocky core or residual heat from its formation. The lower temperatures on Pluto mean that substances like water, ammonia, and methane can exist in a liquid state beneath the surface and erupt as cryomagma. The surface features formed by cryovolcanism on Pluto, such as the domes and smooth plains, are similar to some volcanic features on Earth and other planets, but differ in composition and formation processes. For example, the broad flat domes of Wright Mons and Picard Mons are reminiscent of shield volcanoes on Earth, like those in Hawaii, which form from the eruption of low-viscosity lava. However, on Pluto, these domes are made of icy materials rather than basaltic rock. Other icy bodies in the solar system also exhibit cryovolcanic activity. For instance, Saturn's moon Enceladus has cryovolcanic jets that eject water vapor and ice particles from its south pole, forming plumes that contribute to Saturn's E-ring. Similarly, Jupiter's moon Europa shows evidence of cryovolcanic activity, with surface features suggesting the upwelling of subsurface water through cracks in its icy shell. These examples highlight that cryovolcanism is a common process on icy bodies driven by internal heat and the presence of volatiles. Overall, while the mechanisms and materials involved in cryovolcanism on Pluto differ from those of terrestrial volcanism, the fundamental processes of internal heat driving surface eruptions and reshaping landscapes are similar. The study of cryovolcanism on Pluto and other icy bodies provides valuable insights into the diversity of volcanic processes in the solar system and enhances our understanding of planetary geology and evolution. Sputnik planitia, often referred to as Pluto's heart, is one of the most intriguing and iconic regions on Pluto. This vast, bright, ice-covered plain spans over 1,000 kilometers and forms the left lobe of the heart-shaped Tombaugh Regio, which dominates Pluto's surface. Sputnik planitia is situated on the far side of Pluto, opposite its largest moon, Charon. This region's striking appearance and unique geological characteristics have made it a focal point of scientific study since the New Horizons spacecraft first captured detailed images of it during its 2015 flyby. Sputnik planitia's smooth and reflective surface contrasts sharply with the darker, more rugged terrains that surround it. The plain is primarily composed of nitrogen ice mixed with smaller amounts of methane and carbon monoxide ices. Its relatively young surface, with few impact craters, suggests ongoing geological activity. The region's smoothness is interrupted by polygonal patterns, which indicate convection processes within the nitrogen ice, and by a variety of pits and troughs that hint at complex underlying dynamics. Sputnik planitia's icy plains are not just a static sheet of ice, but are dynamic and active, exhibiting signs of convection and other geological processes. The polygonal cells observed on the surface are a key indicator of convective overturning. These cells, each spanning 20-30 kilometers, are formed by the slow, buoyant rise of warmer nitrogen ice from below, which then cools and sinks at the edges of the cells. This process is akin to the convection seen in boiling water, although it occurs on a much larger scale and at much colder temperatures. The presence of such convection suggests that the nitrogen ice layer in Sputnik planitia is several kilometers thick. The heat driving this convection likely comes from the gradual release of internal heat from Pluto's interior, possibly supplemented by the decay of radioactive elements in the planet's rocky core. This heat is sufficient to cause the nitrogen ice to behave plastically and flow over geological timescales. One of the most exciting hypotheses about Sputnik planitia is the possibility of a subsurface ocean beneath its icy crust. The evidence supporting this idea includes the region's low elevation and the fact that it is situated almost directly opposite Charon, leading scientists to propose that the basin was created by a massive impact. This impact could have delivered enough heat to melt a significant portion of Pluto's ice, forming a subsurface ocean that remains liquid due to the insulating properties of the overlying ice and the internal heat from Pluto's core. Further supporting this hypothesis is the observation of extensional fractures and faults around the edges of Sputnik planitia. These features suggest that the ice shell may be underlain by a layer of liquid water, which allows the ice to flex and move more easily. If a subsurface ocean exists, it would have profound implications for our understanding of Pluto's geological history and its potential to harbor life. The discoveries made in Sputnik planitia have significantly advanced our understanding of geological processes on Pluto, highlighting the complexity and dynamism of this distant world. Before the New Horizons mission, Pluto was often thought to be a static, inert body, frozen and unchanged over billions of years. However, the active geology observed in Sputnik planitia and other regions has upended this view, revealing Pluto to be a geologically active planet with a rich and varied history. One of the key insights gained from studying Sputnik planitia is the role of volatiles like nitrogen, methane, and carbon monoxide in driving geological processes on Pluto. These ices can flow and convect under the right conditions, reshaping the surface and creating new landforms. This understanding has broader implications for the study of other icy bodies in the outer solar system, where similar processes might be occurring. The evidence for a possible subsurface ocean beneath Sputnik planitia also has significant implications for our understanding of planetary habitability. While the extreme cold and lack of sunlight on Pluto might seem inhospitable, the presence of liquid water, even beneath an ice shell, raises the possibility that microbial life could exist in these hidden environments. This idea has parallels with other icy moons, such as Europa and Enceladus, where subsurface oceans are thought to exist and are considered prime targets in the search for extraterrestrial life. Sputnik planitia's active geology also provides insights into the thermal evolution of Pluto. The convection observed in the nitrogen ice requires a source of heat, which suggests that Pluto retains more internal heat than previously thought. This heat could come from the decay of radioactive elements in its core, similar to processes occurring in other rocky planets and moons. Understanding how Pluto generates and retains this heat can help scientists develop more accurate models of the thermal evolution of other icy bodies in the Kuiper belt and beyond. Moreover, the study of Sputnik planitia has revealed the importance of impact events in shaping Pluto's geology. The hypothesis that the basin was formed by a massive impact highlights the role of such events in creating and modifying planetary surfaces. This insight is valuable not only for understanding Pluto, but also for interpreting the geological histories of other planets and moons that have experienced significant impact events. Pluto's atmosphere, though incredibly thin compared to Earth's, is a complex and dynamic system composed primarily of nitrogen, with traces of methane and carbon monoxide. This tenuous atmosphere extends up to 1,600 kilometers above Pluto's surface, much higher than initially expected. The discovery of Pluto's atmosphere has been one of the major revelations of the New Horizons mission, providing insights into the processes that govern the behavior of gases in the frigid outer reaches of the solar system. Nitrogen, the dominant component, makes up over 98% of Pluto's atmosphere. This nitrogen is believed to be in equilibrium with the nitrogen ice on the surface, sublimating into the atmosphere during the daytime and refreezing at night. This sublimation process is driven by the weak sunlight that reaches Pluto, causing the nitrogen ice to turn directly into gas without passing through a liquid phase. Methane, present in smaller amounts, plays a crucial role in Pluto's atmospheric chemistry. Methane gas absorbs sunlight and warms the upper atmosphere, creating a temperature inversion where the temperature increases with altitude, unlike the situation on Earth. This warming effect causes the upper layers of Pluto's atmosphere to be warmer than the surface, which remains extremely cold at around 375 degrees Fahrenheit, 225 degrees Celsius. Carbon monoxide, though present in trace amounts, provides additional complexity to the atmospheric dynamics. It is a stable molecule that can persist in the atmosphere for long periods, contributing to the overall structure and behavior of the gaseous envelope around Pluto. One of the fascinating aspects of Pluto's atmosphere is how it varies between the near side and the far side. The far side, being in perpetual shadow from the perspective of Earth, presents a unique environment where the atmospheric conditions can differ significantly from those on the near side, which receives more direct sunlight and has been more extensively studied. Data from New Horizons revealed that the far side of Pluto experiences colder temperatures and different atmospheric dynamics compared to the near side. The prolonged periods of darkness on the far side lead to more extensive freezing of nitrogen and other volatiles onto the surface, reducing the atmospheric pressure in these regions. This contrasts with the near side, where the daytime heating can cause more significant sublimation of surface ices, increasing local atmospheric pressure. Another difference observed is the distribution of hazes in Pluto's atmosphere. These hazes are formed by the interaction of sunlight with methane and other hydrocarbons, creating complex organic compounds that settle out of the atmosphere. On the near side, these hazes are more prominent due to the higher levels of sunlight driving the chemical reactions. However, on the far side, the hazes tend to be thinner and more evenly distributed, indicating less solar-driven atmospheric activity. The far side also exhibits variations in the atmospheric composition, particularly in the distribution of methane. The colder temperatures on the far side cause methane to condense and settle out of the atmosphere more readily than on the near side. This results in a lower concentration of methane gas in the far side's atmosphere, affecting the overall thermal structure and weather patterns. The study of Pluto's atmosphere has profound implications for our understanding of atmospheric science and planetary weather patterns, particularly on small, distant bodies in the solar system. Pluto's atmosphere provides a natural laboratory for studying the behavior of gases at extremely low temperatures and pressures, offering insights that can be applied to other similar environments, such as those on Triton, Neptune's largest moon, and other Kuiper belt objects. One significant implication is the understanding of atmospheric escape processes. Pluto's low gravity and thin atmosphere mean that it loses atmospheric particles to space at a relatively high rate. Studying these escape processes on Pluto helps scientists develop models for atmospheric loss on other planets and moons, providing clues about how their atmospheres have evolved over time. Pluto's atmospheric dynamics also shed light on the role of seasonal changes in driving weather patterns. As Pluto follows its elliptical orbit around the Sun, it experiences significant variations in temperature and sunlight, leading to seasonal shifts in atmospheric pressure and composition. These seasonal changes can cause the atmosphere to expand and contract, influencing surface conditions and potentially leading to the migration of ices across the surface. Understanding these processes on Pluto can help scientists predict similar seasonal effects on other distant, icy worlds. The presence of complex organic hazes in Pluto's atmosphere has implications for the study of prebiotic chemistry. These hazes, formed through photochemical reactions involving methane, could represent early stages in the formation of more complex organic molecules that are precursors to life. By studying the composition and formation mechanisms of these hazes, scientists can gain insights into the potential for organic chemistry on other icy bodies and the conditions that might support the emergence of life. Pluto's atmospheric data also contribute to our broader understanding of planetary atmospheres in extreme environments. The behavior of nitrogen, methane, and carbon monoxide in Pluto's cold atmosphere provides a contrast to their behavior on warmer planets, such as Earth and Mars. This comparative planetology approach allows scientists to refine their models of atmospheric physics and chemistry, enhancing our ability to predict and interpret the atmospheres of exoplanets and other celestial bodies. Moreover, the variations between the near side and the far side of Pluto's atmosphere highlight the importance of considering regional differences when studying planetary atmospheres. These regional variations can have significant impacts on local weather patterns, surface conditions, and even the long-term evolution of the atmosphere. Recognizing and accounting for these differences is crucial for developing accurate models of atmospheric dynamics on any planet or moon. The New Horizons mission to Pluto has provided compelling evidence that this distant dwarf planet is not a static, inert body, but rather a dynamic world with ongoing geological and atmospheric activity. The indications of such activity come from a variety of observations and data points highlighting the complex interactions between Pluto's surface, interior, and atmosphere. One of the most striking indications of geological activity is the presence of varied and relatively young surface features. The vast, smooth plains of Sputnik planitia, for instance, show few impact craters, suggesting that the surface has been resurfaced relatively recently by geological processes. This resurfacing could be driven by the slow convective overturning of nitrogen ice, where warmer ice from below rises to the surface and cooler ice sinks, creating a continuous cycle that renews the surface. Cryovolcanism also offers evidence of geological activity. The large, dome-like structures, such as Wright Mons and Picard Mons, believed to be cryovolcanic in origin, indicate that Pluto's interior is still capable of producing and erupting a mixture of water, ammonia, and methane ices. These cryovolcanic eruptions can reshape the landscape by depositing fresh material and forming new landforms. Atmospheric activity on Pluto is indicated by the presence of a thin yet dynamic atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. The atmosphere undergoes significant changes with Pluto's seasons, expanding and contracting as the planet moves closer to or farther from the Sun. This seasonal variation leads to the sublimation and deposition of surface ices, driving changes in atmospheric pressure and composition. The detection of haze layers in Pluto's atmosphere also points to active atmospheric processes. These hazes, formed by the interaction of sunlight with methane, create complex organic molecules that settle out of the atmosphere, influencing the surface's appearance and chemistry. The fact that these hazes extend high above the surface and show variations in density and composition underscores the active nature of Pluto's atmosphere. Tectonic activity on Pluto is suggested by the presence of various surface features that resemble those formed by tectonic forces on Earth and other planets. One of the most compelling pieces of evidence is the network of ridges, valleys, and faults observed across Pluto's surface, particularly in regions like Tartarus Dorsa. These features indicate that Pluto's icy crust has been subjected to stress, causing it to fracture and deform. The ridges and troughs in Tartarus Dorsa, for example, are believed to be the result of extensional tectonics, where the crust has been pulled apart, creating linear features. The presence of these ridges suggests that Pluto's crust is not only cold and brittle, but also capable of accommodating tectonic stresses, potentially driven by internal forces such as the slow cooling and contraction of the planet's interior. Another intriguing feature is the large, deep chasm known as Virgil Fossa, which resembles a rift valley on Earth. This chasm, stretching for hundreds of kilometers, suggests significant tectonic activity that has caused the crust to split and create a large depression. The existence of such features indicates that Pluto has experienced substantial tectonic forces, possibly related to the stresses induced by the formation and evolution of its ice shell and potential subsurface ocean. Moreover, the alignment of certain surface features with Pluto's rotational and tidal stresses hints at the influence of external forces on its tectonic activity. The gravitational interaction with its largest moon, Charon, could generate tidal forces that contribute to the fracturing and deformation of Pluto's crust, similar to the tidal stresses observed on moons like Europa and Enceladus. The discovery of signs of potential geological and atmospheric activity has profoundly changed our perception of Pluto, transforming it from a distant, cold, and seemingly inert body to a dynamic and complex world. These findings challenge the notion that small, distant planets and dwarf planets are geologically dead and emphasize the diversity of planetary processes that can occur even in the far reaches of the solar system. One of the key changes in perception is the realization that Pluto is geologically active, with ongoing processes that continually reshape its surface. The presence of young, uncratered regions like Sputnik planitia, alongside tectonic features and cryovolcanic structures, indicates that Pluto's interior retains enough heat to drive geological activity. This activity is likely powered by a combination of radioactive decay and residual heat from Pluto's formation, demonstrating that even small bodies can maintain active geologies over billions of years. The evidence of a potentially subsurface ocean further enhances Pluto's status as a dynamic world. A liquid ocean beneath the ice shell would not only explain the tectonic and cryovolcanic features observed on the surface, but also raises intriguing possibilities about the potential for life. The presence of liquid water, combined with the organic chemistry suggested by the atmospheric hazes, creates a more hospitable environment than previously imagined, making Pluto a more interesting target for astrobiological studies. Atmospherically, the dynamic nature of Pluto's thin envelope reveals that even tenuous atmospheres can exhibit complex behaviors. The seasonal variations, the presence of hazes, and the interactions between the atmosphere and the surface highlight the importance of studying atmospheric processes on small, distant bodies. These processes can inform our understanding of atmospheric dynamics across a wide range of planetary environments, including exoplanets in distant star systems. The signs of potential activity on Pluto also underscore the value of exploratory missions like New Horizons. By venturing to the outer reaches of the solar system, we gain insights into the diversity of planetary processes and the complexity of small, icy worlds. These discoveries broaden our understanding of how planets and moons evolve and interact with their environments, providing a more comprehensive picture of our solar system's history and the potential for similar processes to occur elsewhere in the universe. The groundbreaking discoveries on Pluto's far side, made possible by the New Horizons mission, have significantly influenced the planning and priorities of future space missions. These findings have highlighted the importance of exploring distant, icy worlds in the Kuiper belt and beyond, revealing them to be dynamic and complex rather than static and inert. One major influence is the recognition of the need for advanced imaging and remote sensing technologies. The high-resolution images and detailed data from New Horizons have shown that even small, distant objects in our solar system can have diverse geological features and active processes. Future missions will likely incorporate more sophisticated instruments capable of capturing even finer details and providing more comprehensive data on surface composition, geological activity, and atmospheric dynamics. Another influence is the emphasis on multi-mission strategies. The success of New Horizons has demonstrated the value of follow-up missions that can build on the initial discoveries, providing deeper insights into specific phenomena. For instance, while New Horizons provided a snapshot of Pluto's far side, a dedicated orbiter could offer continuous monitoring, revealing changes over time and providing a more detailed understanding of seasonal and geological processes. The discoveries on Pluto also underscore the importance of landing missions. While orbiters and flybys provide valuable data, landing on the surface would allow for in situ analysis of surface materials, more accurate measurements of geological activity, and direct sampling of any subsurface oceans or ice layers. Such missions would be technologically challenging given the extreme conditions, but the potential scientific rewards are immense. The intriguing findings from New Horizons have spurred interest in follow-up missions to Pluto, as well as missions to other Kuiper Belt objects, KBOs. These missions aim to answer the many questions raised by the initial data and to explore the broader context of Pluto's place in the Kuiper Belt. One potential follow-up mission to Pluto is a dedicated orbiter. Unlike the New Horizons flyby, which provided a brief glimpse of Pluto, an orbiter could spend years studying the dwarf planet in detail. It could map the entire surface at high resolution, monitor atmospheric changes, and study the interactions between Pluto and its moons. An orbiter equipped with radar could also penetrate the surface ice, providing insights into the structure and depth of any subsurface oceans. There is also the possibility of a lander or rover mission to Pluto. Such a mission would face significant challenges due to the cold temperatures and thin atmosphere, but it could provide unparalleled data on the composition and properties of Pluto's surface materials. A lander could drill into the ice to search for signs of past or present cryovolcanism and investigate the potential for microbial life in subsurface oceans. Beyond Pluto, the discoveries have encouraged missions to other KBOs. These objects, remnants from the early solar system, hold clues to its formation and evolution. Missions to KBOs could reveal the diversity of these bodies, their geological histories, and their potential for hosting subsurface oceans. The exploration of KBOs is crucial for understanding the full range of planetary processes in the outer solar system. The discoveries on Pluto have profound implications for our understanding of the Kuiper belt, the vast region of space beyond Neptune populated by icy bodies and dwarf planets. These findings suggest that the Kuiper belt is more dynamic and complex than previously thought, with geological and atmospheric processes that can reshape these distant worlds. One major implication is the realization that many KBOs might be geologically active. The evidence of cryovolcanism, tectonic activity, and resurfacing on Pluto suggests that other large KBOs could also have active interiors and dynamic surfaces. This challenges the notion that these distant objects are simply inert, frozen relics from the solar system's formation. Instead, they could be sites of ongoing geological processes driven by internal heat, radioactive decay, or tidal interactions. The potential existence of subsurface oceans on Pluto has also led to the hypothesis that other KBOs might harbor similar oceans. These subsurface reservoirs of liquid water, protected by thick ice shells, could create environments where life might exist or could have existed in the past. The search for subsurface oceans in the Kuiper belt is now a major scientific goal, as these oceans could provide valuable insights into the conditions necessary for life. The atmospheric discoveries on Pluto, including the presence of a thin nitrogen atmosphere and complex haze layers, suggest that other KBOs could have transient or seasonal atmospheres. These atmospheres, driven by sublimation and deposition of surface ices, could vary dramatically with changes in distance from the Sun and local surface conditions. Understanding these atmospheric processes is crucial for building a comprehensive picture of the Kuiper belt's climatic and environmental diversity. Finally, the geological diversity observed on Pluto indicates that the Kuiper belt contains a wide range of surface features and compositions. From smooth plains and towering mountains to dark, tholin-rich regions and bright icy patches, the variety of features on Pluto suggests that other KBOs could be equally diverse. Studying this diversity will help scientists piece together the history and evolution of the outer solar system, revealing how these distant bodies formed and how they have changed over time. The New Horizons mission has revolutionized our understanding of Pluto, particularly its far side, revealing a host of stunning and unexpected discoveries. Among these, the vast, smooth plains of Sputnik planitia stand out, with their young convective nitrogen ice surface that points to ongoing geological activity. The dark, tholin-rich region of Cthulhu Macula contrasts starkly with these bright plains, showcasing the diversity of surface compositions and processes. The discovery of towering cryovolcanic domes like Wright Mons and Picard Mons suggests that Pluto's interior remains active, with cryovolcanism reshaping the landscape. Additionally, the detection of possible tectonic activity, evidenced by ridges, valleys, and faults, highlights the dynamic nature of Pluto's icy crust. The complex haze layers and seasonal atmospheric changes further underscore the intricate interactions between Pluto's surface and its thin atmosphere. These discoveries have profound implications for planetary science, challenging previous assumptions and expanding our understanding of geological and atmospheric processes in the outer solar system. The evidence of cryovolcanism and tectonic activity on Pluto suggests that even small, distant bodies can retain internal heat and exhibit significant geological activity. This revelation opens up new avenues for studying similar processes on other icy worlds, such as the moons of Jupiter and Saturn, as well as other Kuiper belt objects, KBOs. The potential existence of a subsurface ocean on Pluto has far-reaching implications for the search for extraterrestrial life. If liquid water exists beneath Pluto's icy crust, it raises the possibility that other KBOs could also harbor subsurface oceans, creating potentially habitable environments in the outer solar system. The complex organic chemistry observed in Pluto's atmosphere, driven by photochemical reactions involving methane, hints at the potential for prebiotic chemistry in these distant environments. The dynamic atmospheric processes observed on Pluto, including seasonal changes and the formation of haze layers, provide valuable insights into the behavior of thin atmospheres on other planetary bodies. These findings help refine our models of atmospheric dynamics and contribute to our broader understanding of climate and weather patterns on both Earth and exoplanets. The exploration of Pluto and its far side by New Horizons has underscored the importance of continued exploration of the outer solar system. These distant regions are not merely frozen relics of the solar system's formation, but are dynamic and diverse, with ongoing geological and atmospheric processes that offer unique insights into planetary evolution. The discoveries made by New Horizons have expanded our knowledge and challenged our preconceptions, demonstrating the immense scientific value of exploring these remote frontiers. Continued exploration of the outer solar system is crucial for addressing fundamental questions about the formation and evolution of our solar system. Missions to Pluto, other KBOs, and the icy moons of the gas giants will provide critical data that can help us understand the processes that shaped these worlds and the potential for life beyond Earth. These missions also inspire future generations of scientists, engineers, and space enthusiasts, fostering a sense of wonder and curiosity about our place in the universe. As we stand on the cusp of new discoveries, it is essential to support and advocate for space exploration initiatives. These missions are not just about scientific discovery, they are about pushing the boundaries of human knowledge and capability. By exploring the outer reaches of our solar system, we gain a deeper understanding of our own planet and its place in the cosmos. I encourage you to stay informed about upcoming space missions and to support organizations and initiatives dedicated to space exploration. Whether through public outreach, education, or direct involvement in scientific and engineering projects, your support can make a difference. By investing in space exploration, we invest in our future, fostering technological innovation, inspiring future generations, and expanding our understanding of the universe. Together, we can continue the journey of discovery that began with missions like New Horizons, unlocking the secrets of the outer solar system and beyond. Let's support the exploration of new frontiers, ensuring that the spirit of curiosity and adventure continues to drive humanity forward into the unknown.